Good morning.
Hey, Doug.
Dave and Cheyenne. What are you doing here, Cheyenne? Aren't you usually gone on Wednesdays?
No, I usually work. I do this class from 8 to 10, and then I work from 10 to 1, and then I go to my speech class.
Oh, it was just one day for missing.
Yeah.
Got it. Got to work on my memory. I went into the school after the gym today to fix a couple things, and I couldn't remember my password. We got locked out.
So, do you know how much they're planning on doing in person this fall?
We were planning on kind of everything, but students are definitely seeming to prefer this environment. They're signing up for online like 4 to 1. So I'm going to actually change a bunch of what we're doing in the math department today, actually.
Wow.
Yeah, actually, I mean, what are you guys that are in class right now? What do you guys find yourself thinking? Yeah, let's go back in person. I'm sick of this, or this is actually working and it's more convenient because we don't have to drive and all that stuff. What are your thoughts?
I mean, I see the benefits of online. I guess I'm just biased in the sense that this is a cool class that I'd rather take in person. Like my speech class, I don't care that it's online because I don't really care about it. But this class I would want to do in person.
Yeah, it's nice that you can not pay attention to the classes that you don't want to pay attention to.
Yeah, that's funny because teachers have these conversations and then they do sort of do the same things when they're in meetings that they don't want to necessarily be in. It's kind of nice to be able to turn your screen off. But the other side of it is you can turn off and not pay attention, and you can turn off and still pay attention. So, I mean, it's weird from my perspective because I get some interaction. There's some of you that kind of talk during class a little bit. And honestly, I find myself not caring too much whether your screens are on, although because I can't see all of you. I mean, I can move you guys to my second screen, but then if I look over at you, then I'm, from your perspective, I'm looking sideways. So it seems kind of stupid. So I kind of put you guys next to the screen I'm writing on, except for then I can't see everybody. So I don't know.
I think it would definitely be difficult as a teacher to kind of record yourself, like just talking to a bunch of squares with letters in them. So I can see why a teacher would want to go back in person. I mean, I want to go back in person too. So
yeah, I have mixed feelings about it. I thought students would want to go back a lot more than they appear to. So I don't know. Life's a great experiment from beginning to end. This I know. Let's see. Well, we got two main examples we've got to look at today that I hinted at yesterday. So we are yet again considering solving differential equations with Laplace. So first one to look at is, what if your initial conditions aren't at 0? You have a question like that in your assignment, and it's kind of a nifty way to get around it. And as I mentioned quickly yesterday, let's just make up a quick example here. What did I mention yesterday? I forgot what I was going to say. I mentioned yesterday that, it wouldn't be that weird for this to actually come up simply because, you might not check at time 0 when you see something kind of get moving. And so So let's see, what initial condition shall we give it? Well, let's give it kind of something like, well, at time 2, how about it's 4? So, 2 minutes later, you turn this thing on, you turn this pump on, it starts pumping chemicals into the pool, and then you go like 2 minutes later, you kind of check to see how much chemical is in the pool, and it's 4 gallons or whatever, 4% or whatever that 4 represents. And so, you still want to model, but you just don't have the right initial condition. And so, your first thought may be like, oh, I don't really care. Notice this is a first order differential equation because I thought that might save us a little bit of time. So then you can say, okay, well, let's go take the Laplace transform. So you say, awesome, that would be 6 times, what's the Laplace transform of y prime? It's s times the Laplace transform of y minus y of 0. And there, if you were not conscious, is where the problem comes in, because it's like, oh, that's not good, that's y of 0. But I don't know y of 0, I know y of 2. And so that's the problem right there. Well, let's think about that for a minute. This is actually really easy to fix. So this demands y of 0. We're going to have to figure out y of 0, but you should say, well, that's great, but we know 1, 2, 3, 4. We know this point right here. That's the only point in the graph we know. Remember, the graph may, we don't even have any idea what the graph might look like. It might be some crazy fun curve like this or something like that. And so, awesome. So we're basically saying we wish this point was here. We need to know where it is there. As it turns out, y of 0 is actually right there. Does that make sense? So there's no way to predict that. It totally depends on the graph. You understand what I mean? In other words, graph could be coming down here and doing this, which means y of 0 is way up there. We have no way of knowing where y of 0 is. So how the heck are we going to figure this out? The only point we know is 2, 4. And so what are we going to do? We're in big trouble. Well, it's easy, actually. All we have to do is send our graph, in this case, left 2. Now, you know this from earlier algebra classes. What does it mean to take a graph and slide it left 2 in the world of transformations? What's that code for? How do I say that? In other words, if I had a graph like a parabola, y equals x squared, and I wanted to send it left 2, what would I do to that graph?
Add 2 to the variable, like inside the square.
Yeah, because you want it to go left, which is an x direction, then you got to modify the x in the opposite way that you might think. In other words, left is negative, and so you might think it's x minus 2. But that would move it left 2. So whatever graph you have, you replace x with x plus 2, and that moves it left 2. If you want to move it right 7, you replace x with x minus 7. If you want to move it up 7, you replace y with y minus 7. Every place it shows up, even if it's more than one place. So what does that mean for us? That means we are going to replace our t, because t is our, well, kind of our x coordinate, right? Isn't that true? Isn't this the t is a function, or the y is a function of t graph? So all we have to do is replace t with t minus 2. Plus 2, I mean. So now what we're doing is we're basically saying, okay, well, we can't find that graph, so we're going to find this graph instead. So this is kind of the t graph, and this is the t plus 2 graph. Now you should say, well, that's not going to work because that doesn't go through the 0.24, right? And it's not the same graph. Like, we're after the red graph, we're not after the blue graph, but they are the same graph. It's just slid left 2, right? Okay, well, let's just wade into this and see what happens. because we do need to fix that, I guess is my point. You can't just decide to slide it left 2, because effectively what we just did is said, well, forget that, forget that arrangement. I don't want y of 0 to be 4. I don't want y of 2 to be 4. I want y of 0 to be 4. Well, yeah, but that's just not true. You can't just want that and have it be the case. So basically, I'm gonna have to slide this left 2, do the problem, and then slide it back 2. Does that make sense? When I get all done and I actually find the blue graph, couldn't I just slide it back? And that's what we're gonna do. Okay, awesome. So this much we know. So 6 times the Laplace transform of y minus 3 times the Laplace transform of y. And now on this other side, we have 2t, the Laplace transform of 2t. What was t? 1 over s squared. So isn't that 2 over s squared? And then the Laplace transform of 4, which is 4 over s. Remember, the Laplace transform of 4 is just 4 times the Laplace transform of 1. The Laplace transform of 1 is 1 over s. So it's like the 4 just comes out for the ride. And the same thing happened with the 2. I don't know what the Laplace transform of 2t is, but it's the same as 2 times the Laplace transform of t. And the Laplace transform of t is 1 over s squared. And 2 just comes along for the ride. So magnificent. We got an equation now that only has Laplace transforms of y in it. And we're after the blue equation. So awesome. So let me let you have some time here to get ahead of me. Forget for a second that we're sort of finding the blue graph, which really isn't the right graph. Just tear off down the road. See if you can solve that. And do you understand that because I moved it left 2, now I can say y of 0 is 4. I wonder if people are flaming out. There's only 5 of you in here today. Doesn't seem good. Double check that you didn't screw up the basic algebra. So my question before, just again, I still want to give you some more time, but have you ascertained correctly how to decompose this? So the bottom is already factored this time, so we don't have to factor it. But because there's an s squared down there, at least the book's approach is to say, well, you're going to need something over s squared, but then you're going to need something also over s. As I said at the end of yesterday, that's an easier way to do it. You can also just say as plus b over s squared, and that would do the same job. But this is nicer. And then because the other term on the bottom is 6s minus 3, that's only an s term, then I need only a constant above it as well. So that's what you'd want to decompose this to. And again, now it becomes a problem of, can you find A, B, and C? If you have, you should be able to recognize right now that, yeah, I see why I want to split those up. I love plus signs. You should already be able to see, hey, that's one of those E terms, and 1 over S, that's a constant, and 1 over S squared, that's a T term. So I'm going to have something like 4t plus 7 plus some kind of an E term. Like that's where this is going. So this is a good decomposition. This is what we're after. I recognize all 3 of those in the table. That's what you should hopefully begin to feel.
So when I solved that, I added over the 24, and then I factored out the Laplace transform of y and divided the right side by 6s minus 3.
Mm-hmm.
And my graph is the same as yours, but I have 2 over s squared times 6s minus 3, plus 4 over s times 6s minus 3, plus 24 over 6s minus 3. Is that going to make my work harder?
Yes. It doesn't matter. But in a sense, this is the simplest it could be. So I wisely chose back here, and this is where I think you're talking about, when you added 24 to this side, it makes it easier if I add these together. So I said, hey, I can add these if I have a common denominator, but I got to multiply 24 times s squared top and bottom. And then I just had basically this over this. So it's nice if the top is, you just have one fraction, not, which you should understand is called an improper fraction, as opposed to a mixed fraction, which is a mixture of whole numbers and fractions. So they're harder to work with. Even with numbers, they're harder to work with. So it works just fine, but you're just making your job a little harder. And that's exactly why I chose to spend 3 days on this, because the nuance of how to decompose this takes a lot of practice. And I think you need to see a lot of examples and have a lot of conversation about it. So in order to add these, of course, I need a common denominator. So the b is going to need an s top and bottom, so it'll have an s squared, and then it's also going to need a 6s minus 3 top and bottom. And the 6s minus 3 is going to need an s squared top and bottom. So because I'm guessing correctly, then I actually know this is going to work. There's going to be a number for A, B, and C. I made this problem up randomly, so that means the number is probably going to be ugly. And my advice with all of this is just to go really slow, because you can't afford to make a mistake. Like while you're paying attention to it, get it right. Because if you do make a mistake, when you look back at your work, it's going to be just so hard to find. And so I've got my marching orders now. I've got two fractions that are equal to each other. Their denominators are the same. And so now I can just start looking at the top. And again, to keep your brain straight and also to kind of help me give you partial credit on a test, just because it sort of feels like such a charged environment, this is a good idea. Like say, okay, I got some s squareds here, and kind of mark them out. Like 6bs squared, 6cs squared, and 24. So that means 6b s squared plus cs squared has to be equal to 24s squared. So that's not good because I can't solve that yet. But the thing that's encouraging about this, even before I start, is I'm going to have an s squared term, an s term, and a constant, and that's 3 equations, and I have 3 unknowns, a, b, c. That's why I know my guess is good. Then I've got s terms, 6as. Notice I'm marking them off one at a time, minus 3bs, and that has to equal 4s. So again, I'm not happy because that's got an a and a b, and it doesn't even match the top equation, which had a b and a c. And then I proceed to the constant. Constant equation. And I'm looking up there at my marks. And it's like, oh, good, I got things marked out. Well, the only thing left is minus 3a equals 2. And so there's the first good news in the sense that, oh, good, I don't have to use a matrix to solve this. So I know right now a is negative 2/3. That's cool if I haven't made a dumb math mistake. And now that I know that, of course, I can plug that up here. I'm going to go slow and be careful. That'd be negative 12/3 or negative 4. If I add 4 to the other side, that'd be negative 3b equals 8. So b equals negative 8/3. Now that I know b is negative 8/3, I can plug that in up there to get c. So I never had to use a matrix. Now, are you still able to use a matrix for this? Yeah, this is a 3x4 matrix, you linear algebra people. If you don't trust yourself, or you just have to be careful to notice the top equation doesn't have an a, but you still have to put 0 in for a. The second equation doesn't have a c, you got to put 0 in for c. The third doesn't have a b or a c, so you got to put zeros in for those, and then you wouldn't have to work at this so hard. If I had time on a test, I might do that. So let's see, that's negative 48/3, which is negative 16. If I add it to the other side, I get 40. So c is 40, I think. So we got one of them as a whole number. Double check that. C is 16. Yeah, it's 40. Okay. So where am I now? Well, I guess I can say, if I go back to the other part of this, that the Laplace transform of y is no longer equal to 24s squared plus 4s plus 2 over s squared 6s minus 3. It's now equal to what I just discovered. A is negative 2/3. So negative 2/3 is a. I'm going to write it this way, times 1 over s squared. And b is negative 8/3. Might as well just write minus. I'm going to write minus 8/3 over S, or times 1 over S. I think you understand why I'm writing it that way. And then C is 40. And so I'm starting to see Laplace transforms now. Matter of fact, I can see them really clearly, except for the last one. We haven't had this come up before. What are you going to have to do to the last one to get it to look like E correctly?
Can you pull 40 over 6 out?
Nice job. Like this is S, not 6S. Like that's got to be just one S. So in order for that to happen, what can I, again, what can I do to fractions? Well, I can divide the top and the bottom by the same thing. So if I divided the top and the bottom by 6, I'd have 40 over 6 on top, 6 over 6 here, and then 3 over 6 here. And so I can think of it as 40 over 6, or I guess I could reduce that to 20 over 3. 20 over 3 times 1 over S minus a half. Like now it looks like a Laplace transform. It's got to be 1 on top. It's got to be S on the bottom. And I don't really care what the other number is. And so now I can write this as a string of Laplace transforms. So this first one would be the Laplace transform of negative 2/3 times t. This next one would be, I guess it doesn't matter whether I write plus or minus, Laplace transform of negative 8/3 times 1. The Laplace transform of 1 is 1 over S. So that'd be the Laplace transform of 1. And then finally this last one, which is plus 20/3. Actually, I've been writing the Laplace transform. I've been writing that inside the Laplace transform, although it doesn't really matter. Could put it out front too. 20/3 times, hey, that's E to the what? Don't screw this up. Positive 1/2 t, not negative 1/2 t. And so now, because everything is Laplace transforms, I can take the inverse Laplace transform. Inverse Laplace, which means they're all gone. Y equals negative 2/3 t minus, so minus 8/3. Wait, did I get too many negatives? Yes, I did get too many negatives. That's just minus 8/3. And then plus 20/3 e to the 1/2 t. Bam. And of course, if you, like me, don't like fractions, there isn't any reason you couldn't do this. You could say 20 e to the, and I put this one in front only because it was positive. That's kind of cool, right? Doesn't matter, but that's kind of cool.
Wait, the Laplace transform of 1 is 1 over S. So wouldn't it be 8/3 over S?
No, the Laplace transform of 1 is 1 over S. So because this is 1 over S, then this is just 1.
Oh, never mind.
Thank you for speaking up. We are reasoning about this together. Now, where's my phone? Let's go take a quick look at what the graph of this would look like, just for the fun of it, because we just kind of solve these and say, okay, we're done. But we're not really enjoying the fruits of our labor every time. So let's go enjoy the fruits of our labor this time. Right. Pictures, pictures, pictures. There you are. Bam, bam. So we are saying y is equal to, I think I'll just type it the way, no, I think I won't. Parentheses, I want to put the whole thing in there. 20e raised to the 0.5t. I'll say x here. I don't know why, but I'm just going to say x minus, get out of that, minus 2x minus 8. Close the parenthesis. All of that is divided by 3. That was a plus sign. Back up, divided by 3. Boom. Is this good or bad? So of course, it's just fun to see a weird graph. Again, this is really an E plus a line. So I see the lineness. Don't you see the lineness over here? There's the line-ish part of it. And then notice the effect of E. There's kind of the right side is the E part. But what am I happy to see here?
It comes in at 4.
Exactly. Comes in at the 0.04. We are very happy to see that. It's supposed to, but again, we have not answered the question then, right? Because isn't it supposed to go through 2, 4? And so we have the right graph, don't we? Like, as I said from the start of this, weren't we ultimately back here? We were after the blue graph. So we got it. Went through 0, 4, just like I was supposed to, but that's not the original graph we were after. We were after the red graph. Well, how do you fix that? What do we do here?
Do you replace all the t's with t minus 2?
That's exactly right. I love your tone of voice, David. Like, here's my hypothesis, but I'm not exactly sure. Yeah, we slid it left 2 so that we had a y of 0, which we needed, and then we got our answer, and now we just have to slide it back. So since we slid it left 2, now we just got to slide it back right 2. So extremely important point. Now slide back right 2. Hence, let t go to t minus 2. Replace t with t minus 2, exactly as David said, exactly right. So the ultimate answer to this question then is 20e to the 1/2 t minus 2. Minus 2 times t minus 2 minus 8 over 3. Now you can clean that up if you wanted to and multiply the 1/2 into the t and get 1/2 t minus 1 and negative 2t plus 4, and then plus 4 and minus 8 is minus 4. You could rewrite that, it's fine, but that's not. So, bam. What does that look like over here? Well, let's see if we can pull this off. If I just go in here and throw a parenthesis up there and say minus 2, just to watch it work, what happened? And I put a parenthesis in there, say minus 2 again. Notice it did indeed slide right 2. It's the same exact graph, but now it goes through the 0.24. And so, bam, that's the one we were after. That's kind of cool. So notice it actually isn't that terrible, but you got to understand, one of the awesome things about all the calculus classes is you finally actually have to use all of these, what at the time maybe seemed as boring, kind of boring things to know, like how do you shift the graph up and down and right and left, all these transformations. But here's a practical reason. If you're trying to model something, here's a practical reason to do that. So we're just dragging all these algebra skills up. So it's terrifying because you realize it's pretty hard to hang on to all that stuff. And so here we are needing them, and it's been like a year and a half since you studied that, if you will. But it's also really gratifying to sort of feel like, man, all that time I spent studying that stuff, now I'm actually using it for something that could be practical. That's pretty awesome. Well, I took the time to put this in here, so let's throw that label on there and make this in projector mode so it's all big and beautiful. And don't let us down now. There we go. Let's throw that in the notes since we made it Cool. So you get one question on your assignment like that. That's kind of neat to know. So this baby checks out. The only thing that really checks out, though, remember, is the fact that it went through the 0.24. I mean, that doesn't actually make this right. Remember, if you really wanted to check this, what would you have to do?
You'd have to get the original equation and type, f prime or 6f prime of t and minus 3f prime or minus 3ft equals 2t.
Yeah, that's all right. I mean, and that's a wonderful thing to do. If I take that graph right there, this isn't terrible to do because notice the original equation didn't have any product rule stuff in it. So taking its derivative is not super daunting, but you could just say, well, if I took 6 times the derivative of that equation that I just found and subtracted from it 3 times the equation I just found, would I get 2t? And of course, if this really was modeling something important, because you're a scientist and you're not just doing this because you're a math nerd and like this stuff, that would be important, wouldn't it? Like, I kind of like to make sure, indeed, I have found an equation that fits this model, a linear differential equation. And also, just backing up to the bigger picture of this class, remember there was a time when we solved this exact equation with mu. We divided by 6, and so we'd have to divide everything by 6, and then we used the term in front of the y to find mu, and then we went down that, multiplied both sides, and so forth. I actually want to quickly do that. The reason is because we're about to need it again. Otherwise, I wouldn't do it. So I'll just do this really fast. So 6y prime minus 3y equals 2t. If I divide by 6, that would be y prime minus 1/2 y equals 1/3 t. And so we went hunting for mu, the multiplier, by raising e to whatever that power was, except we had to take the integral of it. Unfortunately, that's an easy integral to take. The integral of negative 1/2 is negative 1/2 t. I wonder if that's a coincidence. Negative 1/2 t. Didn't our answer have negative 1/2 t in it? Well, it had positive 1/2 t. Think about that. So there's our multiplier. So then we came back and said, okay, now that I know my multiplier, I will multiply it by both sides. I'll take negative 1/2 t and multiply it by y prime. I'll take negative 1/2 t and I'll multiply that by 3. So I have minus 3 times e to the negative 1/2 t, and that's multiplied by y, and then 2t times e to the negative 1/2 t. So that's why I found mu. Let's see, did I do anything wrong there? Oh yeah, I did. I'm multiplying it by this statement, not the original one. So that's an easy mistake to make because there was a 6 in front of the original one. So I'm multiplying it by the original one. So that makes that negative 1/2. And then the other side is actually 1/3 t. So one thing you should check, we are going to take a final exam in this class. That's the other reason I'm doing this, is did this work? In other words, is this crazy statement right here actually the product rule having just been taken? And really the question is, if I took the derivative of e to the negative 1/2 t, would I get this? And you should say, oh, yeah, good, because the derivative of e to the negative 1/2 t is e to the negative 1/2 t times the derivative of negative 1/2 t, which is negative 1/2. And so, hey, that is the product rule. Awesome, checked out. So that means I can now rewrite that side as e to the negative 1/2 t times y and write the product rule before it had been taken. And then the other side is left alone. And now I can take the integral of both sides, which makes the right side's derivative disappear. The left side, however, is no fun because I've got to do the integration by parts. It's kind of cool how much we've had to kind of practice all the stuff we've known in calculus before. So I'm going fast here. But if that's my u and that's my v prime, then u prime would be 1, and that's what makes that t go away. We're always happy to see that. And of course, you also should realize, I could go to a table and get the answer to this too, right? It's just kind of cool to be able to do it otherwise. So the integral of e to the negative 1/2 t would be e to the negative 1/2 t, but then I'd be dividing by that derivative. So that'd be dividing by negative 1/2, which is multiplying by negative 2. So that integral that I can't take becomes uv, which is negative 2t e to the negative 1/2 t, minus hopefully an integral that I can take, which is u prime v. U prime is 1, awesome. V is negative 2, can I move that up front? E to the negative 1/2 t. So now I have an integral I can actually take. Beautiful.
Did you forget the t on that exponent, the e to the negative 1/2, after you took the integral of the left side?
Yes, thank you. Thank you. And so I get 1/3. This part is unchanged. And we said a second ago, the integral of e to the negative 1/2 t is negative 2, which would multiply by that positive 2 out front and make it negative 4. And I'm thinking in my mind right now, do I need to add a c to this? I think the answer to that is yes. And so remember, all of this is equal to this. Oops, that's not what I wanted to do. It's all equal to this. And so now I can solve for y by dividing both sides by e to the negative 1/2 t. Notice that's going to cancel it here, which is kind of cool. So I just have negative 2/3 t. And it's also going to cancel it here, which means I just have negative 4. But then that c over there, when I divide by negative e to the negative 1/2 t, that'd be the same as multiplying by e to the positive 1/2 t, wouldn't it? So the question is, I'd say this kind of not kidding at all, but did I get lucky and actually, get the same answer? Oops. The answer is no. I did not get lucky. I got the negative 2/3 t, but I just got 4, didn't I? Anybody have any thoughts on that? I'll just give you a hint. I didn't get it wrong.
Yeah, when you actually plug in the t minus 2, that is gonna give you a positive 4/3 that will add with the negative 8/3 to make it negative 4/3.
Nice. In other words, I'm checking it here. That's the actual answer, right? Remember, there was no shifting here. We didn't shift anything. We haven't even plugged the initial condition in yet. But notice if you scope this out, it's -2 times -2, which is -4. -4 minus -8 is -12. -12 divided by 3 is -4. So it doesn't look like I did screw up. But what about the 20/3? Like what about all this business? Well, let's keep going. So remember our initial condition though was y of 2 equals 4. Well, notice in this environment, we don't care. We don't care if t is 2. Fine, just let t be 2. Y is 4 when t is 2. T is 2 makes that e to the 1, right? I'll put the 1 in there. So what does that make c? 4, it's 8. 8 plus 4/3 is 9 1/3. I think this is right. 9 1/3 equals c times e. That seems really weird. So that's 28/3 divided by e. So 28 divided by 3e. That's c. Don't you find yourself going, what? There's no way that could be right. I mean, that's frankly what I'm thinking right now. Really? So very unconfident that
Wait, how'd you get, so you, in the top equation, you had y minus 2/3 t minus 4. Mine had minus 4/3.
Yeah, the two
Yeah.
fours cancel out.
yeah, so when I plugged in t is 2,
Oh,
that became 4/3 while I was discovering c. But now that I discovered c, I'm putting it back. The only thing I'm doing now is just replacing that c up there. Everything else stays the same. So don't you find yourself going, huh? Can you put those two e's together though? How's your algebra skills? Isn't this e to the 1? What do you do with exponents? If I have x to the 7th over x to the 3rd, what do you do?
Subtract them.
Subtract the exponents. When you take any classes beyond calculus, you should sort of have the constant sensation that you're bad at algebra. Have you had that?
Oh, yeah.
Big time.
I mean, it's just like these rules about exponents, you know the rules about exponents, but would you think to do that, if you will? So, so the question is that the same? Where did you go? Is that the same as that? So that is -2/3 t minus 4. So we got that part right. The question is just, is this part right? Again, it doesn't look quite right, which could mean I made a mistake, or maybe it just takes a little manipulation. Notice that is e to the 1/2 t minus 1. So the e is correct. Is it 20/3? I guess that's the only thing left. Is it 20/3? No. Oh, I forgot the third. There is a 3 down there that I forgot. I got 28/3, and so I think it's wrong. I think I did something wrong. Anybody know what it is? Because I don't.
Doug, out of curiosity, on the test, are you going to ask, solve for the differential equation the old way? Are you going to specify, or are you just going to say, do it any way we can?
No, in this next test, it'll be Laplace. It'll be used Laplace transforms to do everything.
Cool. Okay.
Because that's what this section's about. In the real world, ultimately, it would just be like, do it any way you want.
maybe you could.
Yeah, so there is something wrong. That should be 20/3. Everything else is great except for And by the way, we're actually not even sure which one's right. It could be the green one's right and the red one's wrong. Which again is why, as I said before, the ultimate test is to go back and take the derivative of these things, put it back into the original problem like we described, put them back into that question right there. And, I could determine now which one's right by doing that. Again, I'm trying to get you to think real world here. Like, you're going to make algebra mistakes, but just got to be able to find them. Obviously, fortunately, the only mistake I made was fairly small because they matched pretty darn well, but I made some kind of a constant error somewhere. But notice, as I said before, the trick is to like go slow and not get it wrong, because now, do you feel like I do? Like, how are we supposed to find it? There's like 2 pages of gobbledygook everywhere. It's like I got no chance of finding this. So it's just kind of cool to see that, because it went through the 0.24, that didn't make it necessarily right. Would you agree this one should also go through the 0.24? I mean, didn't we plug that in anyway? No, maybe I made a math mistake someplace in there, but
I graphed them and they both go through that point, but the second one is a little lower. It goes below the x-axis.
yeah,
So-
because basically the constant in front of the e, they have the same e, it's e to the same junk, and then the line is the same, but the constant in front of it is a little different. And the constant affects the slope, and so that one of them is sloped just slightly differently than the other one.
I got for my y equation, I got minus 2/3 t minus 4/3 plus c e to the 1/2 t, and I got 20/3 for my constant.
4/3. So
So-
you're saying,
I'm not wondering if we got.
oh yeah, that's it. Wait,
No, yeah.
yeah, that is it. Notice, so that's the mistake. So notice right here, there's a 1/3 out front, and I saw that with negative 2/3, but I didn't see that with 4. I forgot it from then on. So that should have been, let's go fix it, because this is just kind of cool to do. This is interesting. What about 1/3 times c though? I forgot it there too.
Still just a constant. Still
But it's a
stays the same.
constant, so it actually didn't matter. So it mattered with the 4, but it didn't matter with the c. That's kind of interesting. So yeah, so let's fix that. So let's see, that's really supposed to be minus 4/3, which makes that 4 plus 8/3, which is 20/3. Yeah, there we go. That's it. Boom. And then beautiful things happen after that. But again, notice how did I catch that? How did I catch that?
When you check the graph,
I didn't. Ben did. I would have taken me another 20 minutes, right? I mean, it could have taken me all, I mean, I might have never found it. But again, I asked the question, is your work going to be clear enough on the test that I can, circle that and say something like, dude, distributive law, it's like you've done a ton of math here. It's like you don't know that, but so that's kind of cool. So I did that because we needed to review that mu technique for what I'm about to show you. But also notice it's kind of cool that in the old method, we didn't care that it was at time 0, right? Fine, plug a point in. I mean, that's all we're really doing. Who cares if it's 2, 4? Whereas we care a lot with the plus, right? You got to know 0. Now, of course, as I've said, often you do that. You do because they're called initial condition for a reason. In other words, you know what you started with. I know what I got right now. I test the pool and I see how much chlorine's in it. So I know what it is at time 0. Then I start doing something to it. I start pouring chlorine in or whatever. Start using a UV light and I start doing something different. And I just want to see, how's that gonna change over time? Like, when do I turn it off? I'm hoping you see the modeling aspect of this, because this is why it's so profound in all the sciences. because you look at something and you say, that's not good, let's change it. So then you start effecting some kind of a change as an experimenter. And then all you know then is, I know what it is right now. At time 0, the pool has this much chlorine. And then you affect some kind of a change. And so the only equation you can write is a differential equation because you're changing something. And that's the only thing you know. You say, hey, I'm going to pour in 2 gallons per week now of chlorine. And then, what's going to happen then? Well, I can't write an equation except for the equation of change. And that initial condition will be an initial condition, which is time 0. So that's why this is such a profound concept. Cool, same answer. Just weird how radically different those 2 techniques are, isn't it? And yet they sort of land in the same location. That's just really crazy, I think. And it's so profound. Now I rambled a bunch, but notice that took an hour. Man. Okay, there's one other problem that is in your assignment, but it is probably not going to be on the test, and I think you'll see why, but it's just so cool. I can't not do it. And I assigned it. So I assigned question 36, and if you tried that at all, you should have floundered terribly, unless you used, well, an old technique. But this is just kind of neat. So we're going to do question 37. Because if you can get question 37 right, then you'll be able to get question 36 right. So question 37 says this: if you have t times y double prime minus 2 times y prime plus t times y equals 0. Ooh, good, it's equal to 0. That looked terrible. And y of 0 we'll say is 1, and y prime of 0 we'll say is 0. That's really nice. We love zeros. Now, why is this problem different?
It's not constant coefficient.
Yeah, it's not constant coefficients. And you can't use the mu technique here because that's a second derivative. And so this is actually a differential equation you can't solve. Every time I gave you a second order differential equation, as David pointed out, the coefficients were constants. But now all of a sudden we got t in there. So this is a really complicated second order differential equation. And so it's just kind of cool to think that you can solve it with Laplace transforms. But how are we going to take the Laplace transform of these 2 things when there's not a constant out front? Remember when there was a constant out front, we said, oh, sweet, constants just come along for the ride. But what about t? Well, you should be able to say, you should look at that now and say, well, man, if I take the integral of that constant just doesn't come along for a ride because it's not a constant. If I wanted to take the integral of that, which is really what a Laplace transform is, then that's integration by parts. And so, I can't just pretend that t is not there, pretend it's a constant. This is not good. But in one of our clever dodges down here, we need to look at this one now. I mentioned it to you the other day, but now we're actually going to have to use it. What this says is if you want to take the Laplace transform with something that has a t in it, good news, you get to ignore it. Notice over here, just take the Laplace transform of the function. Except for when you're done with that, you got to take the derivative of it. So for us, n is 1, right? It's t to the first power. So we have n is 1 here. So that's -1 to the 1. So it'll be a negative number. And then it's the Laplace transform just of y double prime, which we know, except for once we get done with that, we have to take its derivative. That's what this is saying. So this is the cool use of that. So warning, this is going to hurt your brain. This whole question is going to hurt your brain. So what is the Laplace transform of t y double prime? From the clever dodge, we are saying it is -1 to the first times just the Laplace transform of y double prime. However, once we get the answer to that, we have to take its derivative. Now, again, it's unfortunate that a derivative and a 1 look the same, right? Because this over here is actually a 1, whereas that second one is actually a derivative. Seems like we could have come up with a better symbol for that. So let's see, what would that be? That'd just be negative. And then the Laplace transform of y double prime, of course, is s squared times the Laplace transform of y minus s times y of 0 minus y prime of 0. Whoa, got excited there. But boom, we've got to take the derivative of that. Weird. And, you know, in this land, we're taking the derivative with respect to s. In other words, this thing right here means dy ds. And let's throw in what we know, just because we don't want to have to take the derivative of stuff that's weird. Y of 0 is 1, y prime of 0, ooh, that's awesome, is 0. So now let's take the derivative of that thing. So what are you thinking when you see this? Oh no, I have to take the derivative of that. What rule should be like bing, springing out in your mind?
Guessing we're gonna need product rule. Yeah.
Product rule. So do you see the product rule there? So notice though, it's very alarming. It says the derivative of the Laplace transform of y. Notice I don't really know what to do with that exactly. However, a Laplace transform is an integral, right? But unfortunately, it's an integral that goes from infinity to 0. So unfortunately, those don't just cancel each other out, because Laplace transform is an integral, but it's a definite integral. In other words, I actually have to stick in infinity and 0 into it to get it to work. So unfortunately, I can't just cancel those out. In other words, part of you might think, oh, cool, that's just y. If I take the derivative of an integral, then I get my y back again. I wish that was true, but because of the infinity to 0, it is not true. So all of that is the product rule. And then I just have the derivative of minus s, which is just minus 1. So there we go. And it's actually minus times all of that. So let's see, to make sure I don't make the same stupid mistake I made a minute ago that Ben rescued us from, I'm going to distribute that in there right now. So there's the Laplace transform of t times y double prime. But again, you should feel very daunted by the fact, like, what have we been doing every time? We've been factoring the Laplace transform out and then getting everything on the other side. But notice this time you have a Laplace transform and a Laplace transform prime. This feels not good. And then we have the Laplace transform of negative 2y prime, which is, of course, much less painful because there's no t there. So we can just say, oh, that's great. That's negative 2s times the Laplace transform of y. And then it would have been just minus y of 0, except for there's a minus 2 in front of it. So that makes it a plus 2. And as before, we say, oh, that's 1. So there's that. And then again, we're not happy to see the next one because it says that we need the Laplace transform of ty, not just some constant. So I'm going to give you a second to write that out. Can you do the same logic that we just did a second ago? What does that t mean and what do I need to do about it? How do I ignore the t? How do I basically not have to worry about the t thanks to the clever dodge?
Or it'd just be the Laplace transform of y, but with the derivative of it.
That's
It wouldn't be
exactly right.
negative. Yeah.
That's exactly right. So I only have to worry about the Laplace transform of y, but unfortunately I have to take its derivative. And I have to say -1 raised to whatever power is sitting right there. Well, that's a 1. So it's basically just negative the derivative of the Laplace transform of y. So I actually have to take the Laplace transform of y, come up with an answer, and then take its derivative. Okay, so this is horrible.
So Doug, Laplace transform of t of y, would that be the same as Laplace transform of ty prime? Because the prime is supposed to be the n is the number of derivatives. So I was confused because this just had y. This is no derivative. Y have no derivatives.
No, it's because what that's saying is the n here is found right there. In other words, it's the exponent of the t.
Oh, I see.
And this is saying you need to take the derivative 1 time then. So this n here is not an exponent. It's telling you how many derivatives. So if that was t cubed, then you would say, okay, it's -1 cubed times still just the Laplace transform of y, but I have to take its derivative 3 times.
Okay, I see.
Good question.
That's
Okay,
weird
so
how that works.
that's crazy. So I have successfully taken the Laplace transform of both sides, and now I can kind of add them all together, right? So I find myself thinking I'm going to screw this up. So there was the first one, and I guess the second ones are obvious. And so now I'm just going to plug it all back in. So plug in, what do I get? I think I'll take the time to rewrite it. -2s Laplace transform of y minus s squared Laplace transform of y, but I have to take its derivative +1. And then I move on to the next one, -2s Laplace transform of y, and then +2. Let's see, I distributed that right. Yeah, the +2, the -2 changed to a +2. So +2, and then minus the last one, the Laplace transform of y, but I have to take its derivative. And that equals the Laplace transform of 0, which is 0. So there we go. But unfortunately, like, I'm not going to be able to factor out. Remember how profound or how cool it was that when you took the Laplace transform of both sides, it took the derivatives away, and all there was a bunch of Laplace transforms. Well, now notice you've got Laplace transforms and derivatives of the Laplace transforms. That is not good. So I'm not just going to be able to factor that out. So what am I going to do? What am I going to do?
Can you take the Laplace transform of the Laplace transform?
Yeah, that's interesting. Like, where are we here? Well, this is the reason why I reviewed this a second ago. What did we do when we had the old way for that problem? We recognized, hey, look, right here, I've got junk prime, and then I've got junk. Remember why at this point was unknowable, some unknowable crazy equation. And as it turned out, it was like, a line plus an e and so forth. So it's some unknowable function's derivative and then some unknowable function. Well, isn't that what we have? Then we have a Laplace transform derivative and then just a Laplace transform. So could I take that mu approach and effectively what did that do? Well, didn't it get rid of the derivative? That's how we, by rewriting it as a product rule, we were able to take the integral of it and get rid of the derivative. That's what we need to do. See if you can see what I mean here. So let's see, I've got the Laplace transform of y derivative, but then, what goes with that? Well, I'm just kind of circling these. There's my Laplace transform of y derivative. And there's another one. And so if I factor that out, you see how it's minus s squared and -1. And that's multiplied. And then I've also got just a regular Laplace transform of y. but switch colors, but there's one there and there's another one there. So if I factor those out, hey, look, it's minus 2s, or just minus 4s. So maybe I'll just write it that way. So I got kind of lucky in the sense that they both added together. And then let's see, that takes care of everything except for, notice there's a 2 and a 1. So there's a plus 3 equals 0. Is that true? Okay, so let me write this in kind of the way that you're a little more used to seeing it. Again, think of that as minus s squared minus 1 times just junk prime. And then minus 4s times the Laplace transform of just junk. So it's minus 4s times junk. And then I got to move that 3 to the other side. Well, do you agree that looks like what we did with mu now? But what did we have to do before we executed the mu program? Remember, we didn't want this here. We didn't want there to be something in front of that. That had to be a 1.
Are you going
So
to divide it over?
Yeah, we had to divide that all away. Also, in terms of just making my life easier, maybe I'll just take care of this simultaneously. But if I divided, I just happened to notice that everything here is negative. Does it make sense? I could just multiply both sides by -1 and I wouldn't have all those dumb negatives. So is that okay? I just kind of thought about, oh, they're actually all positive. And so this crazy animal, and notice this is a book problem. It's not like I just made this up for the fun of it. Like this is one of the questions in the book. So, but you know, to not show you this example, like I'm not sure anybody's getting this question right. So if I go mu hunting, as I like to say, then I've got to figure out what the integral of 4s over s squared plus 1 is with respect to s, and that will be my mu. That'll be my multiplier. But let's go kind of slow here. This just feels like it's so dangerous algebraically and mathematically. I'm going to go slow here. How do I find the integral of 4s over s squared plus 1? Well, to be careful.
Move the 4 out front, take away one of the s's.
Yeah, one thing I could do is pull the 4 out front. You can't take away one of the s's, though. In other words, you can't cancel this and cancel that because you're violating the distributive law, because you got to do it with 1 as well.
Oh, yeah.
Do a u substitution.
Yeah, if I let u, and if I let u be equal to s squared plus 1, and you may remember from integrals, we don't like plus signs on the bottom. So if I can do that, that would make this problem a lot easier. However, unfortunately, I'm going to have to get rid of that ds. And so if I take the derivative of both sides, I get derivative of s squared is 2s times the derivative of s, and the derivative of 1 is just gone. But why am I all of a sudden really happy? Because why is that actually awesome that there was an s left on the right-hand side of that derivative I just took?
Because it matches the SDS in the equation.
Exactly. It matches that s up there. So if that s hadn't been on top, this would have been a really hard problem. It would have been a trig substitution problem. Hopefully that just gave you like a facial tick. Like, oh my gosh, it's been so long, I can't do that anymore. Like we'd have to let s be something like tangent of theta, because tangent squared theta plus 1 is secant squared. Like this would have been nasty. But
I remember those.
Thanks to the fact that there's an s on top. Again, this is just kind of cool to go back and, you know, refresh this. But I could have looked this up in a table. And I think I'm even going to take even even a better approach to this. In other words, don't I have 4s ds over there? Well, if I multiplied both sides by 2, then wouldn't I have 4s ds? So now I'm ready to substitute. And again, I like to kind of have you think a little bit bigger. Isn't that what we've been doing is with Laplace transforms, as we've been substituting? We've been substituting the letter t for the letter s. And so this is a transform. I'm transforming this integral from s to u. I'm taking something I can't do and making it something I can. Okay, so what do I have then? Well, I just have u on the bottom. And if I replace 4s ds over here with that, then I just have 2 du. Hey, that's easy integral to take. That's a good transformation. Now all of a sudden it's easy. The integral of 2 over u is 2 natural log of u. So mission accomplished. Except for now we have to do what we've been doing with Laplace transforms and say, well, you won the fight in the land of u, but there is no land of u. There never was a u. I got to get back into S land. So all I have to do, of course, is switch u back out for what it once was. And so sweet. That's what I just found. Now, where was we? We were trying to find mu, which is equal now to e to, well, that statement right there, because we just found the integral of 4s over s squared plus 1. And we figured out it was this. How's your algebra skills? What are you going to do with that? That's a nasty multiplier.
Move the 2 in front. Is it s squared plus 1 to the second power, and then the natural log and e cancel out?
Nice. Very good, Connor. It is e to the natural log, not linear, natural log of s squared plus 1 squared. Again, that's just an algebra principle, right? If you have a logarithm and 2 is in the front, it could bounce up to the exponent and still be the same exact answer. But now e to the natural log of junk just cancel, in which case this is just s squared plus 1 squared. And so I have my multiplier now, at least I think I do. And again, I always find myself like amazed. Like, really? Is that actually going to work? So I'm going to apply that to that red equation up there now. And supposedly beautiful things are going to happen. So, okay, let's see if beautiful things happen. S squared plus 1 squared gets multiplied by the derivative of the Laplace transform. And s plus 1 squared gets multiplied by 4s over s squared plus 1. Well, doesn't that cancel one of them? So don't I get a 4s times just s squared plus 1? Because the one on top, the 2 on top cancel with 1 on the bottom. You okay there? Times the Laplace transform of y. And then terrifyingly, I have to multiply that by the other side. But oh, look, on the other side, there's also an s squared plus 1 on the bottom. So it cancels with the 2 on the top cancel with 1 on the bottom. And so I just have 3 times s squared plus 1. So the question is, did this accomplish what we wanted? In other words, I'm on the edge of my seat, the drums are rolling. Is this the product rule? Was it successful? How do you tell? Well, if you take the derivative of that, do you get that? What's the derivative of s squared plus 1 squared? The derivative of junk squared is bring the junk down front, reduce that by 1, times the derivative of what's inside. The derivative of what's inside would be 2s. Oh my gosh, it actually worked. 2 times 2 times s, or s times s squared plus 1 to the first. It actually worked. What an amazing technique that mu thing was. Wow, I can't believe it worked. That is amazing. Therefore, we can now underivative that. We can write it in its pre-product ruled, in its pre-derivative form. And so what you're writing is the non-derivatives. Like you're not writing this one, you're writing this one. And over here, you're not writing this one because that's the derivative form. That was the derivative. This was the non-derivative. And then you're saying, I'm going to take the derivative of that based on the product rule. That's kind of hard to like, do you see that? Like, which ones do I write in there? Like, that's not that easy, but it's the non-derivative form of each one. I look at this first one right here and I say, which one of those is not the derivative? Oh, it's this one. Which one of those is not the derivative? Oh, it's that one. And so that's still equal to what's on the other side, 3s squared plus 3. So now what do I do? Well, now I can take the integral of both sides and bam, I just got rid of the derivative of the Laplace transform, which I didn't know what to do with. So I just got rid of it. Wasn't that what we did with mu before? We had y prime and y, and we said, oh, I wish I didn't have y prime. Well, we got rid of it based on this cool mu technique. So now I can integrate both sides. And on the left side, that is wonderful because it just got rid of the derivative. And on the right side, that's a really easy integral to take because the integral of 3s squared is 3s cubed over 3, which is just s cubed, and the integral of 3 is 3s. And I'm not writing it down, but notice we're in the world of s, so I'm taking the integral with respect to s. And so we're finally on our home turf. Well, I don't know if I want to call this home turf yet, or at least a place we recognize. We have the Laplace transform equals ugly junk that we need to decompose. Now, fortunately, question 36 is easier than this, but this one is really nasty to decompose, which again, the majority, half the time in the last 3 days, we've spent just trying to figure out how to decompose stuff because that's hard. It takes a lot of intuition.
You're like a little kid who just saw a store he recognized for the first time, and you're like, oh, I can get home from here. I remember that store.
Exactly. My dad tells a funny story about being in Little League as a kid because in his culture, like kids were almost ignored, just figure it out yourself, you're fine. And whereas now helicopter parents are like dropping their kids off and then staying there and filming them at Little League and then fighting with other moms and dads who don't let their kids play.
Yeah, that's, I mean, I got lost as a kid a lot, and strangers are just like, they'd be like, where's home? And I'm like, I don't know any street names. And they just walk with me for a while until literally I'd recognize the store and I'd be like, I know where I am. We're good.
Yeah, that was my dad's story. He's like, I don't know, just you'll figure it out. And he rode his bike down to Little League practice and then he didn't know how to get home. But he was just riding around.
I feel like nowadays
like
you still can't even do that. Like it's just such a crazy world. I miss being able to do stuff like that. But if I had a kid, I wouldn't let him out.
There's actually a push toward that because people are panicked because there are news stories, but you know what you forget is those news stories are spread over the entire country. You know, so is there something stupid going on? Yeah, but I don't know. Is it worse maybe to not let your kids live at all? Yeah. In the end, you know, it's like my dad did figure out the way home, and that's actually a part of your progress is learning how to solve your own problems. Obviously, there's a balance there, but anyway, have to get off on that tangent. I don't know. Okay. So this is actually pretty difficult to decompose, and the reason is because of that 3 right there, and the reason is because like there was never a 3. Like, look at your table. Is there any of them that have a 3 up there? Is there any cubes? I see some squareds up there, but I don't see any cubes. And so, you know, how am I going to get out of that mess? That's not good. And I will tell you that I played with this myself yesterday for 15, 20 minutes before suddenly the light went on. Like, I mean, I stared at that thinking there's no way to get rid of that cube, and there's nothing that has a cube. And so how am I going to get rid of that? Well, this is good for your knowledge. If you ignore what's on the top, what's your gut reaction for junk that is squared? How do you decompose it when you have junk squared from 7.4 that we skipped? You have junk squared, but you
Erase
also
it.
have junk not squared. In other words, everyone down, isn't that what we did earlier? We had s squared, and so we had an s squared and an s. Well, this is no different. You have junk squared and junk not squared. Except for what are we looking at? We're looking at a squared equation here, right? So what goes on the top is not just an a, it's an a s plus b. In other words, it's one power below that. Because it's a squared term, then I'm going to need an s to the first on top. So what I did is I thought to myself, there's just no way to get rid of that cubed. And I just stared at it and stared at it and stared at it and kind of gave up. And then I thought, well, this is the pattern. So, you know, the question is, would that produce an s cubed? And it will, because I've got to multiply this one top and bottom by s squared plus 1, don't I? To get a common denominator. The left side already has s squared plus 1 squared, and so that would do it. And then I noticed, hey, look, that's, you know, s squared times cs is going to be cs cubed. Like, that'll give me an s term. And so this could actually work, is what I ultimately discovered, even though my initial thought was, that isn't going to work. So I have as plus b for that one, and then I got to distribute. I got to multiply all this together, so I get a cs cubed, and then cs times 1, and then d times s squared, and then d times 1. And so all of that is what's on top of my now common denominator. And so, of course, what I'm trying to do is see, is that numerator, that ugly blue numerator, equal to this red numerator up here? Can I make those be equal? So just for the sake of the notes being good, let's squeeze this in so that we understand what we are trying to accomplish. So I need these two to be equal to each other. So there I go. And so as before, just to make sure I stay organized, I'm going to say, well, what are my s cubed terms? Unfortunately, I see I only have cs cubed has to equal s cubed. So I know c is 1. Like, that's the only cube there is. What about my s squared terms? I see I have a ds squared, and that has to equal, well, look on the right side, there aren't any of those. There's no s squareds, and so there's only one s squared on the left. So I know c is 1, d is 0. That's interesting. What about my s terms? Well, I've got an as on the left and a cs on the left. Notice I'm not crossing those out, which is a little more dangerous. And on the right, I've got a 3s. And so there's that. And so that's not good, because I can't solve that now. And then I've got my constant term. And I've got a b on the left, and I've got a d on the left. And that has to equal nothing, because there is no constant on the other side. And so, okay, what do I do about this? Well, notice that's not hard to do in your head. And so whoever made this problem up was a little bit nice on us, in the sense that they said, well, if d is 0, then notice b has to be 0. So that's kind of interesting. And sometimes, by the way, that means you didn't have to include those. And then if c is 1, then of course that means a has got to be 2. And so that worked. Like, at least I think I decomposed it. And so I can say then that my Laplace transform of y is now equal to as plus b. That's 2s over what as plus b was over, which is s squared plus 1 squared. And then plus over just s squared plus 1, cs plus d. Well, c is 1, so that's just s, and d was 0. So it decomposed into that. And so in a sense, it was like, oh, wow, that's amazing. That cubed went away. Like I was not able to do that. But now I am. Like these are now a little more recognizable on the chart, not perfectly recognizable. You stare at your chart for a second, your Laplace chart. Maybe I'm lucky and they're just there, or maybe I have to modify them a little bit. Hey, that one right there. Isn't it these two? No, let's see. It was s plus 1 squared. It was like junk, and then there was a squared. So it's this one. And then it was just not squared. So is it this? Is it these two? Is that what you're seeing? Or, well, what's on the top? If it's an S on the top, it's this one. But if it's an A on the top, then it's this one. So it's like those, it's those, isn't it? So, hey, this here one being type A, I must crop this off because there's too much ugly stuff there. Isn't this one perfect right now? Like it's done. We got lucky. S over s squared plus a squared. Well, a would be 1. So isn't that cosine of t? So it's the Laplace transform of the cosine of 1t. What about the other one?
It looks good for sine of t sine at.
Yeah, it actually is like I didn't even have to modify it. You see that? It's like kind of lucky. 2as. What's a? Well, for us, a is 1. So if a was 1, that'd be 2 times 1 times s, just 2s. Like it's already done. So it's the Laplace transform of t sine of at, but a is 1. So I won't rewrite all this, but now I can take the inverse Laplace transform, and hence I would just say that y is equal to t sine of t plus cosine of t. Bam. Wow, that's crazy. Amazing. You can probably see that you got to be really careful here. Like if you're the author of a book, you can't just kind of make stuff up. In other words, let me just ramble quickly about the original question here. I don't even know where it was. What would have happened if that had been a squared?
We would have had to integrate twice.
Yeah, does it make sense that this would have become a 2 and then this would have been a second derivative? Well, you may have noticed a second ago we used the mu technique to get rid of one derivative, but now it's like a second derivative. And so, the question is that impossible, or does it require a second course in differential equations? This is ordinary differential equations, and we're going to proceed to kind of a second course that's harder. Does nobody ask that question because nobody cares? Remember, mathematicians do ask those questions because they just, they want to know what kind of differential equations can we solve. But all I want you to see here is notice how dangerous it is when you start throwing the independent variable over there on the left side. And so, we just threw t, but what about e to the t? What if I threw e to the t over there? Well, we do have a clever dodge, if you will, to get rid of that, right? But would that be possible? I mean, this was the nicest foray into the land of throwing non-constants in front of this that you could possibly get. Because notice it's just a t. That's the simplest equation that exists. But what if you threw sine of t in front of it, or t cubed plus 9t, or it just sort of feels like, man, that's a can of worms. And so as hard as that question was, do you notice it's like the easiest question in the land of what if those coefficients are not constants? So in a sense, we opened the door and we saw this new land, and we just kind of like, petted the cat in the door and then shut the door. Like, I don't think I want to go in there. We got one problem right, but it's like this opens up an entire world here. How crazy can we get? And again, this is why at the start of this, I didn't skip it, but I just didn't assign it. It's very important to kind of label, what you're looking at. That's a second order differential equation because it's got y double prime. It's homogeneous because it's equal to 0. And then is it linear? And the answer to that is, actually, I'm suddenly thinking, is the answer to it linear? Linear had to do with whether or not, what these coefficients were. These had to be, yeah, it is linear because these coefficients are the independent variable. So it's okay that these coefficients are independent variables, which are t. But what if you took this away and made it like a y? Now it's the dependent variable. Well, now it's not linear. And the reason for that is because there are techniques to solve these. And we just found one. Like, this problem is incredibly complicated. And I just can't imagine the first person that waded into a question like this and was able to find, like, man, I actually answered that. That's crazy. And for extra credit, yeah, maybe we should just do this. I find myself wanting to check this. In other words, I think maybe we should just do this. We got a few minutes. Let's do it. So supposedly, if I copy the original answer, the original question, supposedly we just found the answer to this second order linear differential equation, right? Supposedly. So let's check. Except we're doing this manually this time. Remember, I reminded you yesterday how to go on to Desmos and kind of just let it do the work for you, which I think is wonderful. But let's not wimp out this time. Let's check it ourselves. So we have y, but we're going to also need y prime. So the derivative, product rule, the derivative of t sine of t, with the derivative of t would be 1 times the sine of t, plus the t left alone times the derivative of sine of t, which is cosine of t. And then the derivative of cosine, thank you for no product rule, derivative of cosine is negative sine. So there's the first derivative. And we also need the second derivative. Derivative of sine of t is cosine of t. We love that plus sign. Derivative of t cosine of t, product rule. Derivative of t is 1 times the cosine left alone plus the derivative of cosine, which is actually negative sine. And the derivative of sine is cosine, and this negative sign just comes along for the ride. And so there's all my ingredients. I got everything I need. And now, of course, we're just on the edge of our seat to plug that back into this green equation and see, does that really equal 0? That just would be really surprising if it was. And so I need to take t times y double prime. So t times all of this business. And by the way, notice there's some simplification there because you have a cosine and a minus cosine. So I have t times the cosine of t, and then t times the sine of t. That doesn't seem very encouraging because remember, this stuff has all got to cancel out. So there's t times y double prime, and then it's just minus 2 times y prime. So minus 2 times, hey, look, sine times minus sine goes away. If I'd been smart, I'd have noticed that before, and that would have made my second derivative easier, wouldn't it have? So minus 2t cosine of t. So that takes care of that, minus 2 times, and then t times the y. So I got to go t times that original y up there. So plus t times the sine of t. That'll be t squared sine of t, and then plus t times the cosine of t. And I'm on the edge of my seat to see, does that equal 0? Does it? Well, I've got a minus t squared sine of t and a plus t squared sine of t. That's really good news. And don't I have one of these plus one of these minus 2 of them? Yeah, it is true. So amazing. What a crazy process. And yet it actually worked. I mean, it must have been fun for the first person that didn't give up. Too easy. That would have been my instinct. Like, it's impossible. I can't figure out how to do this. So interesting. Our brains hurt. So we are going to review / do the project tomorrow. So let's take a quick look. I'll let you out early, but might as well pull the, I'm going to pull the review up. I didn't plan on doing this, so let's just take a second. Midterm 3 review. Man, it's over there. So there's nothing new to learn, but again, the review is me giving you a chance to practice and also me telling you what you actually need to be able to do. So as I mentioned before, based on, I think it was Connor's question, basically I want you to use the Laplace transform to do all these problems, even though we now have a second way. And so most of them are, they're not what we did today. Like what we did today is good for an assignment question, but I'm not gonna give you stuff that's ridiculously hard. But notice you've got a first order differential equation that is not homogeneous over there. You got a second degree differential equation that's not homogeneous, and another one, and another one. Notice what's on the other side, like every possibility in a sense. There's E that's on the other side, there's trig that's on the other side, there's a polynomial on the other side. I mean, I kept it small, I didn't make it a squared equation or whatever. So that's kind of the, the non-homogeneous case. And again, don't forget what's kind of interesting about this is, remember when you were doing these by hand, you had to take a guess and you had to remember the homogeneous answer. Like, does it make sense? You could easily forget that.
Are we going to have any non-zero initial values? Like
No.
y of something that's not zero? Oh.
That's what I'm saying. I want the test to be pretty straightforward. So I'm not going to give you a non-zero initial condition. I'm not going to give you a problem like we just did. I think it's cool to know it. That's why I showed it to you.
Okay, cool.
But I think it's okay to, pass this class with the stuff that's a little more right down the middle of the plate.
Sweet.
But remember that what's cool about Laplace transforms is you know, before you would have taken this question here and you would have said, well, my guess is, you know, a e to the 4t, and then you would take it's like we just did, its first and second derivative and plug it in and sort of, you know, figure out what value for a would force it to become 48. And then, you know, now you found the answer, but you could easily forget there were actually two homogeneous answers, right? Because that factors to y or r minus 5, r plus 2. There were two homogeneous answers. And if you forgot those, as some people did, you'd kind of get the question wrong. Well, the cool thing about the Laplace transform is it throws those two homogeneous answers along with this answer at you, which is really cool. And you don't have to stop and think, uh-oh, does the R value that comes from the homogeneous answer over here, does it happen to match that 4? If it does, then, you know, oh man, I got to make a different guess. That guess won't work. It's got to be a t e to the 4t, and, you know, I got to change my guess. Well, remember, the good thing about Laplace, don't have to worry about any of that. You just got to be able to decompose the nastiness that shows up as a result of taking the Laplace transform of both sides. And that's no joke. Like, that's pretty hard, right? Obviously, you're going to have the table of Laplace transforms, the one that I made, because it's the only ones that you need. I did post the larger one, if you will, that I stole off the internet somewhere. I posted that in my open math as well. But it's got a bunch of stuff in there that we didn't have time to cover and that you won't recognize. And so, and then, you know, what if it's a third order? No problem. And then this last point, be capable of building the Laplace transforms in the table that we regularly used. I'm going to ask you to make one of them. And then we did that clear back at the start. And so you need to practice that a little bit. Go back. And as I said, can you make these basic ones? I will not be asking you for the ones that had to repeat themselves. Which one was that? Was it these? No, that was the really nasty ones. But I would say that any of these are fair game. I should have circled cosine as well, but those are all fair game. You should be able to make those. One of those. I'll ask you to make one of those on the test. Probably not this one. Just one of the simple ones, one of the ones that's straightforward. And you have the sheet, like you know what it's supposed to be. You have up here the definition of what a Laplace transform is. And so, you know, practice those. Own this stuff, as I like to say. Don't borrow it. Don't have to steal it from the sheet. Own this stuff. Understand it. Make sense of it so that when you forget it later, it isn't that hard to rebuild. If this comes up in some future course we're studying. And then the project. So I gave that introduction. So tomorrow I'm going to just start off with the project, and we're actually going to see that. We're going to need that, if you will, which we haven't had to touch here. At least we might need that. I will point out in going out the door, what's the difference between these? If you look at these up here on the right-hand side, and then you look at those on the bottom, look how close they are to the same. Well, aren't they the same? Look carefully. What's different? It's the tiniest thing that's different.
That b value is negative.
Exactly. Notice up here, this is a plus sign. When you complete the square, we only did a problem like this, you got a plus sign there. But what if that came out as a minus sign? All of a sudden, it's not sine, but hyperbolic sine. That's kind of interesting. And of course, that's a door we haven't looked in, right? Hyperbolic sine, what's that? I've never hiked on that trail. That's what you should be thinking. But the project tomorrow is really cool. So anyway, I'll wait to introduce that then. All right. So the other thing you might want to do with tomorrow is you should finish the assignment. When's the assignment due? It's probably due tomorrow, isn't it? Yep. So you can bug me with questions about the assignment. As a whole, certainly tomorrow, you can certainly bug me about those after class right now. And then as soon as I turn you loose on the project, then you can ask me project questions. You can ask me review on the test questions, but as always, my review's already posted and all of my solutions are posted. So you can also solve it yourself and then diagnose your own mistake by going back and looking at it. Since the homework is due tomorrow, which is Thursday, Friday morning, I'll post the solutions to the homework on My Open Math, because remember, I'm not going through and grading every single thing you're doing there. I'm sometimes grading it just based on completion. And on the other times I'm grading it based on the right answer, but I'm not looking at your work. I'm just kind of grading it right or wrong. So you'll have the weekend to kind of look over any homework questions. But again, look the ones over that pertain to the test, because there's plenty of challenging questions in that homework assignment. All right. Stay after, or I will see you tomorrow.
Thank you, Doug.
Thank you all.
Thanks, Doug.
I had a question about the homework. Unless, do you have a question, Cheyenne? You can go first if you want to. I feel like
No,
I
go
was
ahead.
first. Okay. So just